Hey kids, happy snow day. So because I'm going to be out Monday and Tuesday, let's make sure we get some stuff done. So we can still do the lab tomorrow if it should be okay to get in tomorrow. And I think it will be based on what my road looks like. But anyway, this is our unit 8. If you want to follow along, and I believe many of you are asking for a little more support in where to go if you don't understand what I'm saying, and the book, I'm going to follow the book pretty good this next semester. Certainly this unit. So if you want an online book, you can just email me. I'll send you your password and all that. Please do that. It's chapter 6 in the Holt Modern Chemistry book. We're paying for you to look at it. Please take me up on that if this isn't making sense or you want more problems to look at or whatever. So we're talking about chemical bonds this unit, and this all has to do with the Boo Boo Jeffries thing that we talked about last semester, which is Boo Boo Jeffries is an awful fighter. Scorpionox is the amazing fighter. Everything in between is in between those two extremes. As you can see here, Boo Boo Jeffries' weakness is fighting. She's not very good at it. Likewise, when we're talking about bonding, it all has to do with electrons and who gets them. And that is electronegativity. So the measure of an atom's ability to attract electrons. Boo Boo Jeffries of the periodic table is down here. These are the metals. They have very low numbers for the electronegativity. They don't really want to fight for an electron. Up here are the scorpionox things. They will fight you for an electron. Fluorine, oxygen, you should learn. Fluorine, oxygen, nitrogen are the big ones as far as wanting electrons. Hydrogen, remember, even though it's on the non-metal side, on the metal side, is a non-metal, so it would belong over here based on its electronegativity. And the noble gases are out. We don't deal with noble gases for bonding because they don't want to bond. They already have all the electrons they need. So they have full shells. They're very stable and they don't bond for that reason. All right. That all said, let's talk about what is a chemical bond. So a chemical bond is an attraction that holds two atoms together. And it will take, you should have learned that yesterday, that there is an attraction holding two bonds together in the interactive with the PBS. And you should have also kind of learned that it takes energy to break a chemical bond. So pulling any kind of bond together, whether it's ionic or covalent, is going to take energy because they want to be together. Non-metals tend to attract electrons and become like noble gases. Metals have little attraction for their valence electrons, and those are the rules for chemical bonding. So if I want to do that? Let's see what's here. Why do elements bond with each other? All right. So to become like noble gases, elements can't always just do it by themselves. They need help. And the easiest way to become like a noble gas is to get enough electrons to have stable full outer shells. When we're talking about full, we're talking about S&P orbitals, which is 8. All right, let's not get into that too much then. 2 ways to achieve this. Basically, to become like a noble gas, there are 2 ways to achieve this. One, they can become an ion. An ion is a charged particle, so they can lose electrons like metals do and become positive, or they can gain electrons like the non-metals do and become negative. So going back to our look here, these will all want to gain electrons. They have high electronegativities, really want to fight for those electrons. These green ones are the metals. They will not fight for an electron, so they will lose their electrons and become positive. So now the issue is when you have two fighters that are close to each other, what happens? Then you do more of a sharing. So if there isn't a clear winner between who would win a fight over an electron, then sharing becomes more the thing. And that's the difference between ionic and covalent. So just a reminder, valence electrons are the outermost electrons, the ones on the outer shells. And the reason we only say S&P and that there can only be a maximum of 8 is you recall when we were doing this last semester that the row you're in is the energy level. So row 1 here is this one. And you can see there's 2 electrons in there because there's only 2 spaces. Row 2 is this green circle, and it can hold 8 electrons because there's 2 from the S and 1, 2, 3, 4, 5, 6 from the P. So that's a total of 8. 2 plus 6 is 8. That can hold 8. The next level, the third shell, can hold 8 from the S and the P, and then it also holds the D. But you don't put in these D until you put the 4S in. So therefore, these would be the highest shell, and therefore the outermost shell. That's why we don't count D, we don't count F. Remember, it's the row you're in minus 1. So we always put electrons in a higher energy level, so a more outermost shell, before we put inner electrons in like D and F. That's why they don't count. If you don't like any of what I just said, just remember there's 8 maximum valence electrons. Okay, so what type of compound will form? Will it be ionic or covalent? So if you have a large electronegativity difference, that would be an ionic situation. So a large difference, the electronegativity, I've already kind of discussed this, determines how strong they'll pull for electrons. So if there's a large difference in two atoms who are trying to form a compound's electronegativity, then one's going to take away the electron from the other, and you'll get an ionic compound. If it's a small difference, typically when they're both high, meaning that they're both non-metals, is what I meant, then that means they would bond in a covalent manner. So let's investigate this further. So ionic bonding is a hostile takeover, and this was seen on the PBS interactive that we did, that basically one element steals an electron from another element. And you can see here, these two kids are not playing nicely with this toy. This kid basically took all the toy, and this kid was left with not much of anything. They're not sharing. So that is what happens here. Sodium has just the 1 electron in its outermost shell. Chlorine has 7. Chlorine being located in the non-metal corner of things, in the scorpionox corner of things, is going to want electrons. Sodium being on the Boo Boo Jeffrey side of things, the metal side of things, is not going to care much about electrons. So because of that relationship, sodium will lose that electron to chlorine. Chlorine now has a stable outer shell of 8 electrons. And now look at sodium. Sodium also, by losing that 1, has a stable outer shell of 8 electrons. So they're both noble gas-ish. Sodium is positive, chlorine is negative. Now, because of those opposite charges, they attract one another. So covalent bonding happens when sharing occurs. So if you have like hydrogen and fluorine, where the electronegativity difference isn't that great, it is pretty great actually, but they can share these electrons. So hydrogen brought this red one with it, fluorine has its 7, and they share those electrons and they make a bond that's covalent in nature. So let's look at the orbital diagram view of this. If you recall this, remember we would make arrows up and arrows down. So if hydrogen is going to bond with itself to make H2, one arrow up, one arrow down, when they come together, they now think they have one arrow up, one arrow down in the same orbital. And that's what makes this happen. Fluorine, the same thing. Fluorine has a 2p that's almost full, except for the one up, and a 2p you can imagine almost full with one down. So when they come together, they think that last orbital is full because one's up, one down, and they're sharing them. So they spin around. All right. I don't know if that's going to work, but let's see. The other important thing we really got to get down is the formula unit versus the molecule. So when ionic elements, like ionic compounds, like sodium and chlorine again, sodium's going to lose an electron. It has 11 and 11 when it's neutral. It's going to lose that electron over to chlorine. It's going to get smaller now because it has more protons than electrons, so it can pull those in a little tighter. Chlorine's going to get bigger because it has more electrons than protons, so it can't quite keep them in as well. And now that they have opposite charges, this has a -1 charge because there's more electrons than protons. This has a +1 charge because there's more protons than electrons. They're going to attract to one another and stick, and they're going to form this lattice, because once you start this from happening, it's just going to keep going, right? Positive, negative, positive, negative, positive, negative, right? It's just going to keep surrounding every positive with a negative, going to keep surrounding every negative with a positive, and it'll go on for a long time. And that's why we could say a formula unit is just the smallest part of this, the smallest repeating thing. The plus minus, the sodium and the chlorine is the formula unit. Whereas molecules, which are sharing, so there's not as near as much a charge distribution, they don't have that kind of attraction to one another in between. So this molecule and this molecule, they don't have the attraction that a ionic lattice would have. So covalent molecules are going to be able to have a little more freedom, basically. They're less confined as formula units would be because of this charge distribution. These are not as chargey, so they're not as attracted to one another, and it's easier to pull them apart. These are very hard to pull apart because they're plus and minus. And what determines all this? Again, it's the polarity scale. So this is sort of my rule of thumb, but it's just a general, remember, it's all a spectrum, whether this happens or something in between there happens. If you recall, if we go into, since I brought it up, that's not what I want. No, I don't want that either. Hold on a second. Where'd it go? Oh, no. Hold on. Not that. No, sorry about all that. You don't need that. You don't need that. Oh, no, kids. Somehow it got closed. All right. Well, here we are. We are talking about this. So they lose. What was I talking about? I don't even remember now. Sorry, kids. I was talking about, the polarity scale. Right. Isn't it good to be in charge? I thought this was open already. I don't know why. Okay, hold on. Here we go. So if we have a situation like this where they are equal, right? So when they're both equal, there's really no difference in charge between the two. However, as one becomes more and more powerful for electrons, it gets more and more that you see this red color from the negative charge is growing. The partial negativeness of it is growing because it has electrons more. This one we can make even less so. So as the electronegativity is different, it's a very stark difference between a negative end and a positive end. And the closer they are to each other, the less of a difference there is and the more covalent. See, covalent versus ionic here. You have a more ionic character when there's a stark difference, a more covalent character when there's no difference or there's no charge difference, basically. And it can go either way, right? Depends who has the most and who has the least. The charge difference is what makes something ionic. And it was right there. All right, kids. So from current side, so the difference in electronegativity, if the difference is about 0 to 0.4, we're going to call that non-polar, where they share equally. If it's a bigger difference than that, but not quite ionic, we're going to call it a polar difference. And if it's bigger than 1.8, we're going to say it's ionic. So what's polarity? So you can either share nicely like here or non-nicely, like above there. So these kids are not sharing this toy very nicely, but they still both have a hold of it, like if they were electrons. So that's a polar situation. So one has it more than the other. So this kid would be more negative. This kid would be more positive because he doesn't really have them, but they both have a hold on it. It is still a sharing. You can go all the way to non-polar covalent where they're sharing completely equally. And that would be, for example, a completely equal sharing would be like this, right? They're completely equal sharing, but the more the one fights over electrons than the other, you can start getting this, what we call a polar bond. So a polar bond is basically in between that complete sharing and that complete hostile takeover. And that would be the hostile takeover. All right. This is making great sense to me. So there's another kind of bonding, metallic bonding. This is the last. So polar bonds can be, these are basically covalent. Since ionic is already an extreme, we say that these are covalent, the polar and nonpolar. All right, metallic bonding is the last kind. So now if you think about it, metals don't care about their electrons, so they kind of bring electrons to the party and then they just let them run away. You know, parents like this who bring their kids and let them off at the party and then they don't know where they are in 10 minutes. Maybe you don't. Maybe that's an older person problem. However, it's similar if you're a younger kid. Let's say you bring an inner tube to this pool. And sometimes, like, where's a kid who doesn't want an inner tube at this moment? Well, they all have inner tubes, don't they? Here's a kid here's a guy. He doesn't want an inner tube right now. So he takes the inner tube off, lets it float away. He knows when he needs another one, there'll be one that'll be coming around and he can grab it, right? Another way to think about this is if you've been to a concert or something and the beach ball kind of, back up, and the beach ball kind of bounces around, right? And everyone can bring a beach ball, but they don't really want it. So they kind of just knock it with their hand and it bounces all over the place. That's basically what a metallic bond is. They bring their electrons and then they just let them run wild and they may leave with a different beach ball or a different electron than they started with, but they kind of did what they did. All right. And that is all I wanted to talk about, because then we'll talk about Lewis structures, which we'll do on Monday. I hope that was good. Didn't seem very good. Let's find out. Everybody enjoy the snow.